Students, this tutorial is here to help you understand how to process the data in an IB physics internal assessment. So remember the experiment we did for our independent variable, a certain distance traveled by our object sliding down a ramp. For each distance traveled, we measured the time taken with a stopwatch 4 times. We did that in order to be able to evaluate the reaction time for each of you. Okay, so we did that how many times? 9 times, right? 9 times. And for each time we have measured 4 times the time. Okay, first let me put these in increasing order. It's going to be a bit easier to visualize for graphing. So for this, we want to sort the data. We go on data, we press sort. It brings up this window, and we're going to sort. We're going to say that we don't have any headers and that we want to sort in increasing order the column C, smallest to largest, right? So we go from smallest distance to largest distance. So now we should have all our data going from 0.5 meters to 1.3 meters. Yes, done. Okay, next we want to process this data. So let's make a separate table for our process data. Okay, usually in IB they require you to make a separate table for the process data. And I will start my table with repeating the exact same column for distance. So here I just copy and pasted this distance column. Let me first format the following columns, the following headers, so that it looks nice. Okay, I just copy pasted this and made sure that I obtained the same format. So first thing I'm going to do is obtain the average time, and I'm going to call it T average. Okay, T av like T average. And this is the units is going to be in seconds. And for each distance, I'm going to compute the average. So there's a function in Excel that says average, the average between these 4 numbers. Okay, and this will give me the average measurement of time for this distance. Let's center all these so it looks nice. Okay, and now I want to repeat the same formula for all distances. So I just double click on this black arrow on the bottom right. When I go over here, the bottom right of this cell, there's a black cross. Double clicking on it repeats the same formula for all lines. So we can check here that 0.89 is indeed the average of all these values, and that's what I wanted here, okay, for this distance of 0.90 meters. So now that I have the average, remember I want to obtain t squared over 2 because we have the relationship s is equal to at squared over 2. So let's do this, t squared divided by 2, and that's going to be in seconds squared, not in seconds. Okay, and t squared over 2 is equal to, so the equal sign to enter a formula in Excel, select this, which is t, square it, and divide by 2. That's what I obtain. Okay, I want only 2 decimal points, so I'm going to click on that twice, and I obtain 2 decimal points only, 2 digits after the decimal point. Again, same thing, hover over the bottom right of this cell and double click. We replicated the formula everywhere. Again, for 0.90, I indeed have the 0.89 squared divided by 2. That's what I wanted. Okay, now that I have t squared over 2, well, I'm ready to graph s versus t squared over 2, right? But I also want my error bars. I want error bars. I want to know in each case what the maximum value of t squared over 2 was, what the minimum value of t squared over 2 was, in order to evaluate the uncertainty on t squared over 2. So let's do that step by step. First, what was the minimum value of t squared over 2? And then, what was the maximum value of t squared over 2 in seconds squared? And then I'm going to add a last column. Let me do that first. Okay. I'm also going to need, finally, to compute the uncertainty on t squared over 2. Let's call it this way, t squared over 2 uncertainty. And that will be the information needed for my error bars. This also is in seconds squared. Okay, so what's the minimum value of t squared over 2? Well, equal sign. So I first want the minimum value that was obtained in these 4 measurements. So there's a function in Excel that's to find the minimum between different values. It's called min. So I want the min of these 4 values. Okay, and then once I obtain the minimum of these 4 values, I want to square it and divide it by 2. And that's the minimum t squared over 2 I obtained on these 4 values. Okay, so I obtained an average of 0.22, but my minimum value of t squared over 2 was 0.20, which corresponds to this 0.64, the minimum t, squared divided by 2. Okay, let's do the same thing for the max value. So the formula is equal max, the max of these 4 values, which is going to be 0.69, square it, divided by 2. Here I obtained the maximum t squared over 2, which is 0.24. Okay, so in fact, the 0.22 is really an average. And in fact, we're not confident that we have exactly 0.22. Here, in fact, we know that we obtain a value somewhere between 0.20 and 0.24. So this means 0.22 plus or minus 0.02. How do we calculate this 0.02? Well, it's equal to the difference between the maximum and the minimum divided by 2. Okay, the difference between the maximum and the minimum, so the range of the values, divided by 2. And I indeed obtain 0.02 when I round it to the second digit after the decimal point. Okay, now I have these values. All I need to do is to select them. Again, double click with this black cross and it replicates the formula all over the place. I'm done. I have processed my data. I have all I need. I have, for each distance, the t squared over 2 and the uncertainty on the t squared over 2. So what I need is really these 3 columns here to draw my graph. I don't need the rest. The rest was just intermediate steps into my processing. So here I selected these 3 columns. Okay, to do this, in fact, select the first column and press Control. And while you have Control pressed, you can select the 2 other columns, and this allows you to select all 3 columns at once. Then I'm going to copy this content, copy, and I'm going to paste it in another sheet. Okay, I selected sheet 2 here, and I'm not going to copy it just this way. I'm going to copy the values, otherwise it's going to do something weird. Okay, you need to copy the values here. So you right click and in paste options, you select values and it's going to copy the values. Let's click and I'm done. I have my values. Okay, this looks a bit gross. Let's reformat it the way we wanted. So with 2 digits after the decimal point and all of this. Okay, let's make it a bit pretty. Green background, white, bold, everything centered, and let's have a little bit more space here. I select the 3 columns and give myself a bit more space. Done. Okay, I have something that looks nice here. I have my 3 columns that I need for graphing, and I'm ready to graph. So how do I graph this data? First, I select my 2 sets of values, my 2 columns. I'm going to graph s versus t squared over 2. So actually this is not in the right order because I want t squared over 2 to be my horizontal axis and s to be my vertical axis. So let me rearrange that. The horizontal axis should appear first and the vertical axis should appear second. So this is the order that I need to have. Okay. Let me put this all here. Okay. Good. Now I have everything in the right order. So now I'm ready to select my data and click on Insert. So this is the first step to create my graph. Insert. And I want to select a scatter plot. Okay, a scatter plot will plot a data point for each set of 2 measurements. Okay, so select the whole data, click on scatter, and I just want the points here. I don't want any line here. I don't want any of this. I just want the points. I just want to plot the points. So I click on this one, and this is what I obtain. I obtain this graph. Let's make it a bit bigger. All right. So first, I'm going to select this series 1 thing. I don't need this thing, so I'm just going to press delete. And I'm left with what I need. Now I need to format this graph. So I go on layout, and I want to add some titles here. Okay, this graph, we're not aware of what it's actually talking about. We need to specify what it is. So in layout, you have something called chart title. I'm going to add a title above the chart. Boom, it appears. And I'm going to call this S versus t squared over 2. Okay, I'm graphing S vertical axis versus t squared over 2 horizontal axis. This needs to appear in the title of my chart. And I can say that this actually corresponds to an object sliding down a ramp. Okay, and now we understand what we're talking about. Let's make that a bit smaller. Here we go. Okay, so that was my overall title. Go back on layout, and let's now define titles for our axes. So vertical axis, okay, horizontal axis first. I want a title below the axis, and this is t squared over 2. T squared divided by 2 in seconds squared. Okay, feel free to pause this video whenever you want so that you have the time to follow on your own and do this same thing on your own Excel sheet. Okay, the goal for you is to really practice this. So my horizontal axis, the title is t squared over 2. It's in seconds squared. The vertical axis, let's go back on axis titles. Vertical axis, okay, I like to select this one horizontal title besides the vertical axis. And what is this going to be called? S for distance, and it's in meters. The distance in meters. Okay, let's make the text a bit bigger so that we all see what it is. I just select all my charts, go on home, go on the font here and define it to be 14, for example. Okay, now it's bigger. Now I can read better, right? Especially for you who are watching the video. It's a bit more neat this way. Okay, now we're getting to the critical point where we're actually going to make sense out of this data and use it to answer the purpose of our experiment, which was to measure the acceleration of this object sliding down a ramp. And the acceleration is the gradient of the S versus t squared over 2 graph. So how do I find the gradient of this line? Well, first I need to draw the line. Okay, and drawing a line, making connections between all these points here doesn't make any sense, right? These points are not exactly on a theoretical graph. So here we're in experimental physics. We need to make some approximations and some averages. So here what we're going to draw is called the line of best fit. It means that it's the line that fits as well as we can all this data. Okay, it's approximately going to go through the data this way. It shows an overall trend of this data. And to obtain this trend line, Excel is very handy. You just need to right-click on any data point, and then press on Add Trend Line. And when I press on Add Trend Line, it's going to draw automatically the line of best fit. Okay, we want a straight line of best fit. We're always going to use straight lines of best fit in internal assessments in IB. And what I want is to display the equation on the chart, because once I'll display the equation on the chart, I'll actually obtain the gradient and therefore the acceleration of that object sliding down the ramp. Okay, I'm done. I'm going to close this window now and see it drew the line of best fit here, this black line, and it gave me the equation of this black line, which is very nice because now I have the gradient, so I obtain the acceleration. Okay, the problem is that I really don't like this way of presenting things that much for two reasons. First, the numbers are way too precise here. Okay, it's sure that I wasn't precise up to 0.0001 meters per second squared, right? That's absurd. So first, I'm going to reformat the numbers and round them. So this acceleration, I'm going to round to 2.5. That seems reasonable, 2.5. And this y-intercept, so the intercept here, we actually got a very good intercept because we were very accurate. Okay, it's supposed to go through 0 exactly, and in practice it almost went through 0. Let's round that to 0.001, okay, to express how accurate we were here. The second thing I don't like about this expression is that it makes the variables y and x appear. Okay, y and x don't mean anything in this context. What it means here is the vertical, whatever my vertical variable was and whatever my horizontal variable was. Okay, so let's name them by their actual names. So my vertical variable is s, distance, and my horizontal variable is t squared over 2. T squared divided by 2. Okay, so the equation of my line of best fit here is s is equal to 2.5 t squared over 2 plus this 0.001 thing, which expresses our experimental accuracy. So let's forget about that for now and just focus on this s equals 2.5 t squared over 2. This means that my acceleration, the acceleration I measured actually, is 2.5 meters per second squared. So we can remember that. Okay, let's actually write it down here. The acceleration was found to be 2.5 meters per second squared. Okay, 2.5 meters per second squared. Now, we're not done. We're not done because we want to know how precise this 2.5 meters per second squared is. Is it 2.5 plus or minus 1 or plus or minus 0.1? Where are we at here? Okay, how do we do this? Well, we're going to use all this data we have here about uncertainty on our measurement. We know that distance was relatively precise, very precise, so precise that on our graph here, the error bars on distance would be negligible. So we're not going to have any vertical error bars, but we know that our t squared over 2 had a significant uncertainty compared to the values, and therefore we want to draw the horizontal error bars. Okay, how do we do this? Let's select the graph, go on layout. This is where the error bars, this is where you can find a way to show the error bars, and it's here, right? It's where it says error bars. Click on that and then select whichever one you want. It doesn't matter because we're completely going to change it anyway. So select, for example, this thing, error bars with standard error, whatever. Click on it, and then you have error bars appearing. Okay, these are clearly not what we want because, okay, first there are vertical error bars, so select these vertical error bars. We don't want them, so press delete. And now we're left with these horizontal error bars, which are just given a fixed value here. So we want to change that. We want them to correspond to whatever we found here. Okay, so let's select these horizontal error bars and right click on them. Okay, right click on the error bars and click on format error bars. You have this window appearing, which is a way to format the horizontal error bars. We want them in both directions. That's fine. Yes, let's make a cap appear on each end. It's nice. And we want to customize the value of the error bars. Okay, so let's specify the values. We want the positive values to be these. Okay, and we want the negative values, let's delete this thing here, the negative values to be this as well. Okay, the positive values and the negative values both be this. So for example, here it's going to give a t squared over 2 of 0.22 plus or minus 0.02. That's what it's going to do now. Press OK, and now close, and we have the error bars we wanted. Okay, let's check, for example, for this measurement at 0.5. So at 0.5 here, we obtain 0.22, okay, which is this point. And indeed, plus or minus 0.02. This is what this bar expresses. Okay, this is indeed a bar that goes from 0.20 to 0.24, so we're good. This is exactly what we wanted. And there's something reassuring here is that our line of best fit goes through all the error bars, and that's what it's supposed to do. If it doesn't go through all the error bars, it means that there's something quite wrong with our experiment. Okay, so that's good, that the line goes through all the error bars. Now there's something that we don't need anymore. It's actually these blue points. These blue points don't serve any purpose, so let's get rid of them. Okay, and to get rid of them, I'm going to right click on one of them, and say format, click on format data series, and these markers, I'm going to say none. I don't want any markers. Okay, close, and now I have a graph that just shows my error bars. That's all I want. Okay, I know that each of these values are somewhere within these ranges. Okay, let's move that a bit. Good, looks nice. So now we need two more things. We need to show the shallowest possible line and the steepest possible line, so that we get the shallowest possible gradient and the steepest possible gradient, so that we actually get the range, the value between which the acceleration is found. Okay, our acceleration is not exactly 2.5, it's somewhere between two values. And to get these two values, I need my steepest line, which goes from here to here, and my shallowest line, which goes from here to there. At least this is how the IB expects you to do it. Okay, it's a simplified way of finding the shallowest and steepest lines. Okay, so first I need to find this point here and this point here for my steepest line. Okay, let's start with the steepest line, and I want my left point and my right point. And for my left point and right point, I need to find t squared, well, yes, t squared over 2 and s. Well, the left point for s, of course, is 0.5, and the right point is 1.30. These are the coordinates, the vertical coordinates for the left point and the bottom point and the top point. Okay, and now what's the t squared over 2 value for these? Let me center all that stuff. Okay, format it a little bit. So my steepest line goes from this left point to that right point. So this left point has coordinates 0.22. Okay, this is 0.22 plus the uncertainty, right? So it's here that I want. So here I want my left point 0.22 plus the uncertainty. That's where I want my left point to be. And my right point, I want this one. So I want this value, 0.49. So the 0.49 is here, it's in the middle. 0.49 minus the uncertainty. Okay, minus the uncertainty. Let's make sure we get that right. 0.49 minus the uncertainty on the 0.49. Let's do the same now for the shallowest line. So I'm going to repeat a table that looks like this one with a left point and a right point. My left point, again, the vertical coordinates are going to be 0.5 and 1.3. That's easy. And now the horizontal coordinates. So for my left point, we're now talking about a shallowest line. My shallowest line goes from here to there. Okay, so I want it to go from this left point, so 0.22 minus the uncertainty, 0.22 minus the uncertainty, and I want it to go all the way to that right point, which is 0.49 plus the uncertainty. 0.49 plus the uncertainty. Okay, let's center all these values. Now I have the coordinates of 2 points for each line, for the steepest line and for the shallowest line. Okay, so I have all I need now to draw these two lines. Let's go for it. Okay, the way we do this is that we select the graph. Okay, you select the graph, right click, and click on select data. This select data button takes me to this window, which allows me to add other lines on the same graph. And to add a new line, I'm going to press add. Okay, you could have guessed that. Add, and the x values of the steepest line are the t squared over 2 values, and the y values, let's get rid of that, the y values of the steepest line are 0.5 and 1.3. Good, press OK, and OK again. Now I have my steepest line. And I'm going to add a trend line so that it joins these 2 points and gives me also the gradient of that line in which I'm interested. Okay, so add trendline, display equation on chart, close, and now I have the gradient of my steepest possible line. It's 3.5, right? So I'm just going to write that. This is the only information I need. I don't care about this minus 0.3, whatever. Okay, so 3.5. So here I'm going to write maximum gradient equals 3.5. That's the information I want to keep. Let's put it in bold and maybe another color in blue. That looks nice. All right, so that's my steepest possible line, which has gradient 3.5. This is my average line, okay, the line of best fit, which has gradient 2.5. And now I'm going to draw my shallowest line. Let's go for that. All right, again, right-click on the chart, select data, add the x values of t² over 2 for my shallowest line are 0. This is 0.20 and this 0.52. Y values, let's get rid of that and put 0.5 and 1.3. Press OK and OK again, and I obtain, okay, it doesn't appear here, it's invisible, but in fact it's really here. I obtain the 2 points here for this shallowest line. Right click on one of these points, add trendline. Okay, draws the shallowest possible line, display the equation on chart. And actually, the shallowest line in this case, okay, we can't see it here. Let's bring it right here. The shallowest line is 2.5, just like the average. Okay, that happens sometimes. The shallowest, the line of best fit can actually have the same. It's somewhere between the shallowest and steepest, and sometimes, well, it happens. It can be very close to the shallowest, or actually exactly equal. Okay, so what I want to write here is the min gradient is equal to 2.5. 2.5. Okay, let's put this in bold, give it a color like green so that we make the difference between these 3 different things that we wrote, these 3 different important results. All right, so we found the acceleration to be 2.5 meters per second squared. Let's put that information down there. All right, move that up a little bit. Okay, and now here I'm going to write my main results here. So I found A to be equal, let me scroll up a bit so we see the whole graph. We found A to be equal to 2.5 meters per second squared. We found A minimum to be equal to 2.5 meters per second squared as well, right? And we found the maximum A to be A max to be not 2.5 but 3.5 meters per second squared. How do I find the uncertainty on A? So let's call that A uncertainty. That's equal to what? That's equal to 3.5 minus 2.5, so the max minus the min, divided by 2. And boom, 0.5. So my uncertainty is around 0.5 meters per second squared. Let's write it, 0.5 meters per second squared. Okay, and this is my final result here, 2.5 plus or minus 0.5 meters per second squared. So in my conclusion, this is what I will use. It's not the only thing I'll conclude about, but the purpose of our experiment was to find the acceleration. It was to measure the acceleration of an object sliding down a ramp, and we found the acceleration to be equal to what? To be equal to 2.5 plus or minus 0.5 meters per second squared. Meters per second squared. I'm just going to copy paste that so I don't have to write it again. So that's the way you write your final answer to this experiment. We measured the acceleration to be equal to 2.5 plus or minus 0.5 meters per second squared. This 0.5 expresses how precise we were in the measurement of our acceleration. Another way we can express the uncertainty here, instead of it being in absolute terms, is in relative terms. And for that, we need to express in percentages what this 0.5 is compared to this 2.5. So let's make a little calculation here. 0.5 divided by 2.5 is equal to what? It's equal to 0.2. If I put that in percentages, it's 20%. So I found my acceleration that's another way to write it, I found my acceleration to be 2.5 plus or minus 2.5 meters per second squared, 2.5 meters per second squared, plus or minus 20%. And that's what we call a measurement of relative precision. Our relative precision was 20%, okay, which is not that great, but that's with the equipment we had, that's basically what we were able to do. We were able to measure this acceleration of 2.5 meters per second squared, but we have a level of confidence that's plus or minus 20% or plus or minus 0.5. So the measured acceleration is somewhere between, let's say, 2 and 3. And that's it. That's the whole process that you'll need to apply in pretty much every single internal assessment that you'll be doing during these 2 next years.